Alright, so in Unit 5, we're starting to get into spherical units and cylindrical units and converting them. Again, look at my review. I either learn a diagram or memorize all the equations in order to figure out what you need to sub into in order to get from rectangular to spherical or spherical to cylindrical, whatever it happens to be. So now we have an equation which is in cylindrical. We're going to convert it to spherical coordinates. So looking at this, knowing that rho is equal to x squared plus y squared plus z squared, I know that I want to expand this z minus 1 squared, which then we'll have x squared plus y squared plus z squared minus 2z plus 1 equals 1. 1's cancel out. And now this right here can become rho squared. Now I need to find out for my substitution for my z. So if the relationship between z is, so this is the positive z, this is our rho, this is the angle phi, because again, remember, phi is the angle between rho and the positive z-axis. So this is my equation here. I'm going to top this off with so this right here is considered r, so this is a right angle. So if I want to figure out what z is with respect to rho, then that means it's going to in angle phi. The z is adjacent to this angle, so that means I want to have to use cosine. So z over rho equals cosine phi, because remember, adjacent over hypotenuse, and then z is going to equal rho cosine phi. So now this is right here is going to become rho squared minus 2 rho cosine phi equals 0. And now I can cancel out one of those rho's. And don't worry about canceling them out. We already have rho equal to 0 as a point on this graph, so we don't need to label it. So it already contains rho equals to 0. So that makes our equation now rho equal to, and I'm moving this to the other side, 2 cosine phi. So this is our equation. This already contains rho equals to 0. So we don't need to worry about saying rho cannot equal 0, whatever it happens to be. So now the next one, we have to convert z equals the square root of x squared plus y squared over square root of 3 to spherical coordinates. So this one's not as easy as the first one. So it's going to take a little bit more intuition. So we can use cylindrical as an intermediate, meaning that we're going to substitute in for cylindrical and then go from cylindrical to spherical. Because if you're looking at this right now, we already solved for z, so we're going to go ahead and substitute z in for that rho cosine phi. So this becomes rho cosine phi. And we know that x squared plus y squared is normally r squared, so it's the square root of r squared over the square root of 3. And now r, looking at r over here, if we wanted r related to rho, so instead of it being cosine phi, it'd be sine phi. So r over rho equals sine phi, which then makes r equal to rho sine phi. So then I can replace this. So this becomes r over square root of 3. Don't worry about magnitude of r. R is always positive. So you don't need to worry about this. Not saying that r can't be negative, but in the case of this, it doesn't really make it, it doesn't matter. R is always considered an absolute value. It just changes the direction of it. So then we can replace r with that rho sine phi over square root of 3. So then we have rho's cancel out on both sides here, and then we can then say sine phi over cosine phi equals tangent phi, which equals the square root of 3. And in order to calculate that, think about, so sine phi, so it's going to be square root of 3 over 2 over 1 over 1 over 2. Looking at that on the unit circle, so if this is pi over 2, this is 0. So we're going to have a 1/2 and a square root of 3. So 1/2 for our cosine and a square root of 3 for our sine. So 1/2 square root of 3 over 2. So that's going to be about a pi over 3. You gotta memorize that or find a way to figure it out. It's Calc 3 at this point, so I don't feel like explaining that. So that's what that angle here is, phi. So when I do so tangent phi equals square root of 3, which then implies phi equals pi over 3. So now these are our two equations. Now we need to sketch the solid that is bounded above by the first one and bounded below by the second equation. So phi pi over 3 is a cone. So this is the bottom of the cone. So this angle from the z-axis out to this line here is always going to be pi over 3. So that angle phi equals pi over 3, that's just constant all the way around. So if I were to just draw pi over 3 in infinitely without being bounded, it'd look like a weird arrow glass thing going on forever and ever and ever. But in this case, it is not, so it's bounded. So it's bounded below by this cone and above by rho equal to 2 cosine phi. So there's a couple of different weird ways to think about it. So thinking about phi, or cosine phi, whenever cosine is 0, it's at its maximum. So it's going to look like, so a cosine of 0, rho is going to equal 2. So we know that at the very top it's going to be 2. So say this, we'll say that's 2. And as we go down, it gets slowly smaller and smaller. So when it comes to pi over 3, it's going to be cosine of cosine pi over 3 is 1/2. So this will come down to rho equal to 1. So this right here is rho equal to 1. It's not exactly centered, but it's close enough. So kind of how I know that it's going to look like this is that it's looking like this dome is that when we look at the original equation, it's x squared plus y squared plus z squared. So x squared plus y squared plus z squared, that's a sphere. This minus 2z, it's a little offset, so that it looks more like an egg, something more oblong than a sphere. So now we have, and this right, I'm gonna write down the equation. Rho equals to 2 cosine phi. So now that we have both of our equations, phi equal to pi over 3, rho equals to 2 cosine phi, and then sketch into our ice cream cone, now we need to find the volume of the solid. So the volume of the solid is going to equal a triple integral of, so it's going to make sure you always include, when you use spherical, you have rho squared d rho sine phi d phi d theta. So now we need to find our limits for rho. So for rho, you start out in the origin and you go outward. So no matter, so we start in the cone at the origin. So that means we have to include rho equal to 0. Then we exit out this blue dome. So that means we're going to exit out 2 cosine phi. And then for sine phi, so sine phi, we have to start from the center of, or from the positive z-axis and go outward. And we exit out this this pi over 3, this cone. The reason why I don't exit out the blue portion is because that angle is defined, the angle of this blue portion is defined by the angle of this cone. So that's why we have to use this cone as our defining angle. So we start at phi equal to 0, because again, we include the positive z-axis, because we start in the cone at phi equals 0, and we exit out pi over 3. And then for d theta, we look on top of this say we had yx, we're looking on top of this, it's going to be a circle. So we're going to have to include all theta. So we're going to start from 0 to 2 pi. So this is going to be from 0 to 2 pi. All right. I could solve for this, but I'll just go ahead and tell you the answer for, what is this, unit 5? Answer is just 5 pi over 4. That should be a length cubed. So it equals 5 pi over 4. I'm rushing because I'm trying to do all this before the SI session, so everyone has time to get all the good stuff. So now for this Jacobian is also magic. You basically you have something too difficult to integrate. You're just got too many integrals. You can't solve for it, so you use Jacobian to convert it into a new coordinate system that's easier to calculate, to solve for the integral. So Jacobian, JUV, is going to equal, I always include, it's partial of x with partial of x with respect to u, partial of y with respect to u, partial of x with respect to v, partial of y with respect to v. So make sure you put these absolute value bars. These absolute value bars mean that you're finding the determinant. So partial of x with respect to u is going to be 1/2. Partial of y with respect to u is going to be 1/2 as well. Partial of x with respect to v is going to be negative 1/2. Partial of y with respect to v is going to be positive 1/2. Finding the determinant. So cross multiply and subtract. It's going to be 1/4 minus a negative 1/4. So it's going to equal 1/2. So that's our Jacobian determinant. So every time we take an integral within the Jacobian integration system, we always have to use 1/2. So now we need to sketch the UV region. So in order to do this is by subbing in your x and y into each of these equations here. So in this y equals x plus 1 equation, you can, so this is going to be, so we're going to take this equation 1, this is 2, 3, 4. So equation 1, I'm going to sub in y, so we have u plus v over 2 equals u minus v over 2 plus 1. Then we're going to be able to cancel out the u over 2's, and then I want to have 2 of the v over 2, so I want to add the v over 2, so I want to have v equals to 1. Now look at my second equation. We have y equal to 2 minus x, so we have u plus v over 2 equals 2 minus u minus v over 2. So again, whatever to be considered the same here. So in this case, the v's are the same, so the v's will cancel out. We have a positive u and a negative u, so we're going to add the u over 2 to the other u over 2, so I have u equal to 2. Third equation, where I have y, so u plus v over 2 equals u minus v over 2 equals, or minus 1. So cancel out your u's, add your v halves, so we have v equal to negative 1. Fourth equation is y minus, so we have u plus v over 2 equal to u equal to 1 minus u minus v over 2. So your v's are the same in this case because you have a negative v. So cancel out those. You have a positive v half and a negative v u half. So add those together, so we have u equal to 1. So now these are our 4 equations that we're going to use in our new coordinate system. So u equal to 1 is going to include this portion. So this is u equal to 1. If we have v equal to 1, this is going to include this portion. We have u equal to 2, which is going to include this portion. And then we have v equal to -1, which is going to include this portion. So now we have this box here, our region, which is now G. This is our new region. Now I need to solve for this double integral in terms of u and v. So so we got this. So we have the double integral, and since now we're trying to solve this in Jacobian units, so we have to include our 1/2, our Jacobian determinant, and then we have y squared. So I'll have u plus v over 2 squared plus r or minus r x squared. So I'm going to put this 1/2 on the outside. You have u minus v over 2 squared. D, so now it just becomes du dy. So in order to solve for this is going to become, I want to pull out the 2's here, so they're squared, so it becomes 1/8. So I want to have u squared plus 2uv plus v squared minus, so this is going to become u squared minus 2uv minus v squared, or plus v squared du dv. Oh, I don't know why I had a y there. dv. So if you look, these u's will cancel, these v's will cancel, and then we're left with 1/8 of, and this becomes a plus 4uv du dv. So looking at our units for our u, it's going to be from 1 to 2. Looking at our units for our v, it's going to be -1 to 1. And that's just going to be 1/8. There. It's going to end up canceling out. It's going to all equal 0. So, yeah, trying to speed this up here. Hope the setup here helps. I don't know if you'll have a Jacobian or not, but there's a good chance. But good luck on your test. Move on to the next unit.